So we're going to move on to the next session, or section, I should say. We're going to talk about a panel on integrated photonics. So there's no question that most, and hopefully everyone in this room, loves photons. But why do it in an integrated fashion? What are the challenges? What are the limitations that we need to take into account from either a materials processing side, from a technology standpoint, and where do we need to go? So thank you, first of all, to the panel. From farthest to closest, Stefan Prebble from RIT, Alex Tate from Princeton, Jack Carolyn from MIT, Zach Vernon from Xanadu, and Michael Lear from AIM. So we've got about a half hour. We're a little shifted on time, I know that. I know we're standing between this and a coffee break, so if people throw things, that's okay. I'll be a target, that's okay. So I'm gonna give everyone on the panel 4 to 5 minutes to discuss how they feel about this, what's their thoughts, and then we're gonna open up to questions for everyone in the audience. And we'll start with Stefan.
So I'm Stefan Prebble. Some of you saw my talk yesterday, so you have a pretty good idea of what I do, but basically quantum integrated photonics, and it's definitely one of the reasons I'm up here. So I think one of the challenges is not just universal to the quantum integrated photonics field, but really integrated photonics in general, which is still integrating all these things together, getting lasers on there, and in particular for quantum, the challenge is going to be making sure that we're able to filter that laser light out, and that applies to both nonlinear approaches, but also ones where you have emitters, where you potentially need to be pumping with a laser. So that's maybe why we should be looking at electrical injected single photon sources as well. So it was exciting to hear that AIM maybe doing that down the line. Packaging is obviously the huge issue. Our own group is putting a lot of effort into doing that. We're scaling up circuits, like you saw on the last talk, the collaboration with MIT that many of us have with these essentially matrix operations. There's just so many elements to control, and we're putting huge amounts of effort into doing that. We could integrate essentially CMOS circuitry with these in a low-cost way. I think that will really move the field forward. And then I think the other big challenge is the ability to put single photon detectors. I think the bigger challenge is getting rid of any of the pump light in the first place. And there really hasn't been a robust scheme to get the extinction that you need, get all that scattered light away. And then on top of that, the best detectors are the superconducting ones, so then operating all this at cryogenic temperatures is still a big challenge for the field. So.
Okay. Thank you, Stefan. Alex?
Hi, I'm Alex Tate, and I'm actually coming from NIST Boulder, although I am a private citizen now, which is why I'm with Princeton, which is where I did my PhD about a year ago. And so at Princeton, I worked on neuromorphic photonics, which is this classical computing that uses analog signals to do these types of processing tasks that people find very useful for machine learning nowadays and have other uses out there. And so we're doing something like that at NIST, but it's based on an entirely different material platform. So I work at NIST with Rich Mirren and Seiwoo Nam. So most of you can just tell by the names that we make detectors, single photon detectors that work at cryogenic temperatures. And so something that we're doing that I'm involved in is putting these detectors integrated on silicon on insulator waveguides. And then we've also been working on all silicon light sources that work below 40 Kelvin. That's collaborating with Dr. Paparao at SUNY Poly. And so the thing that we want to do is open up this platform, this cryogenic photonics platform, to the general public sometime in the not too distant future. And this is something we think is really exciting for quantum applications and neuromorphic applications, because there's a lot of similarities in terms of platform technologies and platform challenges that they share with each other.
Thanks, Alex. Jacques?
Okay, thanks. So my name is Jacques Caroline. I'm from the Quantum Photonics group at MIT. And half of what I do is kind of develop large-scale silicon photonic hardware for quantum and actually some classical applications. And then the other half I do is kind of thinking about the different types of applications that we can do along the lines of kind of machine learning optimization and also in terms of quantum simulation. I think it's a really exciting time to be involved in integrated quantum photonics, particularly, for example, with AIM, we can start developing really large-scale circuits. We're at the, at the scale of having a few hundred now controllable optical components on a single device. This in itself starts presenting quite a serious systems engineering challenge, okay? How do you begin doing electrical control of order 1,000 voltage or current sources? And I feel probably that many of us in the room are actually solving these problems and kind of reinventing the wheel. So what I think is interesting is to kind of advocate for a way in which we can kind of share these resources, share these solutions in which we're coming up with these problems. I think it's fascinating to see how losses are coming down in these systems. We heard some amazing kind of, we're in the 1 dB range for things like silicon, and even much lower for silicon nitride. I'm super excited by having the capability of having now silicon nitride in silicon photonic foundry processes. What that means is we can start thinking about doing visible and also having incredibly low loss operation. For me, what I think is one of the most exciting challenge areas is how we can start integrating non-foundry components into these foundry devices. Okay, can we start thinking about putting, indium arsenide, indium phosphide, quantum emitters, okay, which emit around either 1300 or 1500 in silicon photonic circuits? Can we think about getting chalcogenide phase change materials on these circuits, or directly integrating S and SPDs? So for me, these are the really exciting challenges in integrated photonics at the moment.
Thanks, Jack. Zach?
Yeah, so I'm Zachary Vernon. I work for Xanadu. I'm on the hardware team there, quantum startup in Toronto, and we're developing continuous variable quantum optical technologies, quantum photonic technologies for quantum computation and simulation. So the biggest thorn in my side is loss. I think a lot of this stuff has to be integrated in the near term if we're talking about spatially encoded circuits. Colleagues have certainly touched on a lot of the problems there. I'm sure it's an issue in all those other suites of issues, but loss is number one. I think actually on-chip loss, just the raw propagation loss numbers, are kind of okay. I think that in terms of the near-term stuff, we're where we need to be. I don't think any process advancements are really needed in that sense. You talked about silicon, Jacques, and you've talked about silicon nitride. In a sense, that they kind of turn out to be the same. Silicon is higher loss propagation, but the components in silicon nitride are longer. It's lower confinement. So it ends up being about the same for the similar depth networks. A much bigger problem is the bottleneck of going off chip. Stefan mentioned the integrating detectors. Would be fantastic if we could. It does come with a whole host of problems. My personal interests rely on transition edge sensors, so the cooling requirements for those in the near term are even more sub 100 millikelvin. I'm not so interested in full integration right now. I don't think we need it, or at least for the applications that I'm interested in. But what's needed is packaging, and that's another thing that Stefan touched on. The bottleneck is really going off chip, and then in the post-processing, the filtering, needing extremely good outcouplers, edge couplers, being able to, spatial mode converters to go between the mode size on chip to fiber mode sizes, and then the band rejection filters to do very low loss, high rejection, and selective filtering. So if, given where chip technology is now, I think that if we could just solve this outcoupling problem and be able to get 60 to 100 edge couplers working with each 90+% coupling efficiency to single mode fiber, and I think even the filters, sort of the WDM is kind of almost where it needs to be commercially. Amazing things can be done. So I'm most interested in packaging as the key bottleneck.
Thanks, Zach. Mike?
Okay. So maybe I'm just sort of responding to a large extent to the previous guy's comments here. I mean, obviously we have the ability, in principle, to integrate all these things on single chips or on the wafer. We do have a program looking at SNSPDs. Pops is going to talk about that tomorrow. We can entertain different wavelengths, but today, and I mentioned that yesterday, we are 1310 and 1550, and changing the material system is really something that doesn't come easy in a line like ours. So one of the pleas I have for this entire community here is to help us understand where there's a convergence of needs, because we can do a few of these, but we can't do them all. Again, I just want to give you a simple example of what it takes in a manufacturing-like facility like ours to introduce a new material is typically for something as simple as a transition metal. It is a 9 months endeavor, and I don't need to explain to you what that costs in terms of how many wafers I need to run to satisfy the other partners on site's concern that I'm contaminating this thing and they can't do their work anymore. For something more obnoxious, such as a safety hazard, we can take up to 2 years, and we're really talking multiple millions to get this in there. So I need to hear consensus for new materials, whether they're like chalcononides or something else. As I said, almost anything is conceivable. The only thing that I'm violently opposed to is gold, because people will kill me if I put that in the line. That's what we have in our tap facility in Rochester, so we found a solution for that, but it won't be in the silicon line. There are other things. Silver isn't particularly welcome, as you might imagine, and radioactive I haven't gotten myself to, although I'm told that there are some very low-level radioactive substances that might be beneficial if you do ion trapping. So point is, we're more than happy to work with folks. Please be aware that I am not as flexible and agile as, say, a Cornell facility would be, but I will give you stuff that looks the same every time you get it, and I will give it to you at a fairly rapid pace. I showed you some of the cycle times that we have in mind. In the terms of the active programs that we have, I didn't speak about it yesterday, but we do have a program that will attach a control electronic chip to a photonic fabric. Again, it would be up to the community to maybe get together and decide if there's some generic design that you want to send to a TSMC to have that built, or Global Foundries. And we don't care about the source, right? But we can attach these things to the photonic die, and having a source like that definitely allows you to control all these things. There are, as you might imagine, difficulties, because the models that you get from foundries typically don't go down to 4K or 77. It probably doesn't make much of a difference for silicon once you reach that temperature. So that has to be looked at. Are there startup problems for that die if it's at that temperature? But we do have a program to attach these things. We do have a program on single photon detectors. I did mention the laser. That is also a fairly expensive endeavor, so we're asking for federal support on that. But that would lend itself either to amplifiers or single photon detectors down the road, not in the next 2 years. But in principle, down the road, we can integrate all these things.
Thanks, everyone. Okay, now let's open it up to questions from the audience. Anyone have any questions for our panel?
This is like the KGB.
Yeah, I think you guys did a good job of at least presenting the challenges you think there are regarding the development of quantum technology, integrated photonics. But I was wondering if you can comment about some of the design tools you guys might use, and where you guys might see a wish list of how to improve your research process, how to improve your design process from a numerical and computational perspective.
Okay. Who wants to start? Alex?
Yeah, so I think a big question that is kind of happening now is this graphical user interface versus script-driven programming. And there are, when you start getting to larger and larger systems, you just can't do it by hand. It's just way too complicated. And so, but script-driven programming is difficult for its own reasons. It's very opaque. And so I think that something that will be important in the near term is for people working around large-scale silicon photonics to come together and like make an open source, script-driven layout and integrating numerical nightless extraction, kind of make a new version of that for photonics.
Maybe I can make one comment kind of on a different angle. Just as a kind of case study, we've been, at MIT, have been fortunate enough to be involved in a tape-out with AIM Photonics that has been led by the Air Force guys and Stefan at RIT. And this has been an absolute pleasure to be involved in because we've managed to benefit from a kind of collective and collaborative PDK. So that means you don't have to, each individual person doesn't have to redesign every element. We can kind of use this collective knowledge, and that's been absolutely amazing to be involved with. So I don't know if that necessarily answers the question, but I think that's going to be critical going forward, is that we're starting to share these resources between each other.
I just add, sort of transmit a message that I'm learning from my team on the design side. I want to second what Alex said, the sort of scripting compatibility, in particular a Pythonic interface for seamless plugging in of various modules to talk, have numerical talking to, in our case, IPKIS and various other internal simulation scripts talking to MEEP. Very, very important to have. I think Python has emerged in almost all fields now as the way to do this. So seamless Pythonic integration of the various components is an important component for us.
Yeah, one thing that I just want to stress too, I think, I just want to add one thing, that a plug-and-play PDK is going to be a necessary piece, I would say. Even if those plug-and-play elements have some tunability, you can tweak them. You can tweak them through a GUI, not having to go through scripting. I think that would open up the field to a lot of people. Yes. Next question.
How do you deal with process variability in at 4K or at low temperatures? You can't use thermal tuners. So how do you tune your ring resonators? How do you adjust for the variability in the manufacturing process at cryogenic temperatures?
Yeah, that's exactly right. The thermal coefficient of silicon drops at low temperatures. So, but there are other effects that you can use to tune the refractive index, such as carrier depletion or injection or optomechanical type properties. But of course, those are not as strong as thermal tuning. So if you were to make a microring at basically any silicon process that exists today, you wouldn't be able to get it within the tuning range that you could have at 4K, we think. Now, this is something that we're actually researching at NIST to try and develop these things. So maybe we'll have updates.
I'm personally interested in a MEMS sort of approach, because if you could mechanically move something with electrostatic force within the distance that you waveguide, you could engineer it so it's adiabatic and such, so relatively low loss. They've demonstrated this at Berkeley with switching networks. So I think that's something that we should be looking at a bit more out of the community, and it would be nice to have that through a foundry. I think that's going to be definitely one of the paths for doing it.
Even electro-optic on a chip, too. The integration of that would be nice.
Yeah, just very quickly, and another thing that we're interested in at MIT is trying to demonstrate this DC Kerr effect at cryogenic temperatures. And the idea is that you apply either a large electric field or some strain field across silicon. You can break the symmetry of the crystal, and you can get some electro-optic effect. Now, this is still an open question as to whether, whether it's actually a real Kerr effect or whether there's some kind of carrier effects going on. So of course you've got to be really careful about how you measure this, but it's a very interesting research direction.
Okay. Yeah.
So one of the things that's so important about the design environment that's been so successful in integrated electronics and is emerging and becoming successful in what we might call classical or semi-classical integrated photonics You got the PDKs, process design kits. You've got the foundry. But along with that, the people that develop the devices and the people that run the foundry they construct very careful parametric models of different devices so that you can actually run a simulator of the circuit that you've laid out. So the question is, when I start laying out the quantum circuits of the future, do I need a quantum computer to actually simulate it? Is there a chicken and egg problem when it comes to the simulation of these?
So, for photonics, I think in terms of quantum computing is actually unique, where a huge amount of your characterization can actually be done via classical laser fields. So for example, if your circuit is described by a unitary matrix, of course there's loss, so it's not unitary, you can actually characterize that transfer matrix just using classical laser light, and it's incredibly efficient. So my strong belief, and I think what is a real strength of photonics, is that you don't need to do full quantum process tomography, which is incredibly costly to characterize these types of systems.
Yeah, Attila, and then Papa.
All right, so my question relates to the choice of materials. We saw several presentations that in order to have a photonic integrated circuits or any kind of integrated circuits to do quantum information science, computation, communication, whatever it is, you need single photon sources, you need entangled photon sources, you need photon manipulators, you need detectors. And Mike Fento will talk about that we need quantum memory for most functions. Light-matter interaction is different for any of these functions. And Mike Lear mentioned that silicon was chosen for photonic integrated circuits traditionally, coming from the communication industry, and that kind of forced many of the user fields to follow that wavelength. I know that they have different fields that they addressed, from RF photonics to communication to chem biosensors, beamforming, and they created teams to answer the need for those fields. But because of silicon photonics and the wavelengths, I don't know which one was forced on the other. Hey, we have silicon photonics and you'll use this because we have the manufacturing capability, or because the most efficient way of doing those certain fields requires a different wavelength. So to have an efficient detector, you need certain materials that are more efficient at different wavelengths than 1310 or 1550. So my question really is, which industry forces the other to conform? The choice of materials will force the photonic integrated circuit industry to move to another wavelength and another choice of material, or because the existing infrastructure from AIM or another institute, will force everybody back to 1310, and then you will have to face these wavelength converters or the others. So which way do we drive this?
I mean, the answer is not black or white, just like quantum, I guess. I mean, the ideal scenario is that there's a debate or discussion between, opposing ideas. I mean, if you were trying to introduce material systems that are really incompatible, very difficult to introduce into a line, it's just a question of how much is it going to cost and what's the benefit, right? So if there's a choice to be made that might be slightly suboptimal, but can be much easier introduced, I mean, I would vote for that. But as I said, it's not black or white. I mean, as I said earlier, we're more than happy to entertain what ideas are out there, and we're willing to say, hey, look, this solution is really hard, that one is a lot easier, can you live with the other one? Some sort of a compromise probably is needed. And I mean, we're talking about silicon technology, but I mean, I also want to make sure that everybody understands we're using silicon just as a substrate, right? I mean, it is just a convenient substrate, the tools are fit for it. But the materials we're talking about here have very little to do with silicon. I mean, nitride and maybe polysilicon waveguides are just about the only thing that we are sort of reusing, and we had to redevelop these things significantly differently for lower losses, right? So it really is deviated quite a bit from your classical semiconductor technology. We're just taking advantage of the infrastructure base and the tool processes, and if you can rely on applied materials to give you a tool with a process to start from, it just makes it so much easier.
What about from the other end? I mean, what if in the industry you drive this to different materials that cannot be done?
Then you find somebody who can, I guess.
Any other thoughts on that question?
Well, I guess the way I like to think about it is that it's a little bit of both. At first, you have silicon photonics, which is kind of an old idea, 1986, but it really took off when the datacom industry was like, okay, we need fiber optics, but they need to be way cheaper than long-haul communications, and so those kind of fit together, application and material system. Quantum computing is not the justification for having, the AIM foundry or IME or IMEC foundry, but this field benefits a lot because we get a lot of that investment for free and like very solid platform to work on. And so going forward, it'll be interesting to see, like you mentioned, single photon detectors. You don't need those in a data center to do fiber communication. So that's going to fall outside of this like core economic thrust that's sort of been propelling this along so far.
Okay. Last question is Paul.
I think the progress has been incredible, and this is really the way to go. It's enabling technology, integration, I mean. The question is, and I think it's a little bit provocative here, but I think that's why we have a panel, right? When do you think we'll cross over into sort of computational regime where other technologies are like trapped ions and superconducting qubits with photonics?
I could try to take a stab at it. I think, in my view, that's some of the biggest problems facing non-photonic quantum computation. I mean, most quantum computation is not photonic. All these companies that are looking at Google, IBM, Rigetti, all superconducting, IonQ, and Honeywell now as well, doing trapped ions. They're, I think, very good up to a certain size, but that problem is extremely open. The transducer problem, I wasn't here yesterday, but I think there was a talk on that, is maybe one of the most important ones, going into optical bands from microwave in order to do that. The interconnect problem for ions maybe is a little more optimistic, but I think the record is still for going transduction from a trapped ion qubit to a single photon is still around 1%. So if you were to concatenate that and go in and then out and then back in, it's something like 10 to the minus 4. I think that's maybe a good justification to more seriously take photonics, pure photonics, as a platform for doing quantum computation is the interconnect issue.
Okay, but my question was, let's consider photonics as a standalone technology and forget about interconnecting. I mean, we have to be honest. In photonics, we are behind these large companies, Google and IBM, right, and IonQ. So they routinely have 10, 20 qubit circuits. Granted, they're not perfect, but we cannot demonstrate similar size optical circuits quite yet, right? So the question is more like, when do you think, with all the integration work that's been going around in the last 5 to 10 years, do you think we will ever be able to catch up with other technologies, or that's more of my question?
Absolutely. I mean, in terms of circuit sizes for companies like IBM, 72 qubits or whatever, I think a linear optical network on 72 modes is achievable with current propagation loss and reasonable loss levels. Also, it should be mentioned that those qubits that the sort of superconducting people talk about are not fully connected, even remotely. They're sort of nearest neighbor connections, or maybe just next nearest neighbor. So they're very, very limited graphs that can be done, very limited gate depths. When we talk, and I think internally when we all say something like 72 photonic modes, we automatically, I think, we were more honest with ourselves and say, we have in mind fully connected, so a 72, but deep interferometer, which is 72 squared optical elements. So if we are to compare ourselves with the kind of connectivities that those approaches have, I think we're our optics is already on the same level. And the 2 qubit gate issue is definitely more of a problem. The nonlinear elements, that's probably more we're behind. But in terms of sizes, no. So I think a lot of work needs to be done on things like feed forward on detection and using detection in order to induce nonlinearities that they have kind of for free.
Do you envision like 72 photon coincidences?
Sorry, what was that?
Do you envision 72 photon coincidence measurements?
The echoes, did you get that?
Do we envision 72 photon coincidence measurements?
Yeah, in CV at least, that's no problem. we are measuring already tenfold coincidences at hundreds of hertz using CV.
I just want to make one quick comment on this, is that the metrics are very different as well. You know, with superconducting qubits with ion traps, you add one more superconducting qubit, you add one more, you know, you go from your Bell state to a JZ state, and you just keep adding them more. Photonic quantum computing just isn't like that, and the way we're envisioning architectures for large-scale photonic quantum computing doesn't work like that. You know, if you give me an on-demand source of GHZ states, you've done it. You've basically built a photonic quantum computer. Okay, now how you go about doing that is, of course, non-trivial, whether you do multiplexing, whether when you use some kind of cluster state machine gun via some kind of emitter, there's a whole host of different ways you can do that. But the metrics are very different. It's not this kind of linear addition of qubits, which you see in other platforms.
If I could tag on, I think it's an excellent point, Jacques. And maybe the reason I see that what's unique about photonics is the ability to do time-encoded approaches. Because a qubit, we use bosons, right? Bosons can be in the same place at the same time. So another way to think of that, we have pretty good optical buffers, right? Delay lines are easy. They're flying qubits. Other approaches, ions, superconducting, you know, one qubit is one physical piece of matter, and it's stuck and it sits there. For photonics, you can transmit them and you can time multiplex. So a single fiber can contain. A good example is the work of Akira Furusawa in Japan, who has demonstrated 1 million nodes and entangled modes in a 1D cluster state dual rail. Now, it's not fully connected, obviously, otherwise we'd be done. But I think that holds the record for any kind of entangled system at all, and it's in optics. So in terms of sheer sizes, when you think about the compatibility with time encoding, photonics is unique.
I'll push back on that because it's 1D chain of nearest neighbors. So it's effectively you can solve. It's classically simulable problems.
Stay tuned for the 2D. It's coming.
Okay, just in the interest of time and coffee, apparently, let's thank our speakers, thank the panel.